Hello students, I Shakti Kumar, lecture chemistry. Today going to start a new topic from class 11th unit 2, that is structure of atom, and the name of topic is dual nature of matter. Here in this topic I will cover two concepts. First is de-Broglie's concept, and thereafter I will cover the Heisenberg's uncertainty principle. So let's start the topic first, de-Broglie's concept.
Now, dual nature or dual behavior of matter. According to de-Broglie equation, the light energy exhibits dual nature, that is, particle nature as well as wave nature. The light energy propagated in terms of photons or quanta to have particle characteristics and shows phenomenon of interference and diffraction considering to have wave nature. So, on the basis of these facts, light exhibits dual nature, that is, particle nature as well as wave nature. Louis de Broglie conceived the idea that matter in general and electrons in particular may show the dual nature both as particle as well as wave. When Louis de Broglie in 1923-24 conceived this idea, he was guided by the observations of Planck and Einstein on the dual nature of light. On the basis of these guidelines, he could say that matter in general and electrons in particular may also show the dual nature, that is, particle nature as well as wave nature. Now the derivation part. According to Planck, energy of photon is given by relation E equal to h nu, where h is Planck's constant, and nu is frequency of radiation. H Planck's constant and nu is frequency of radiation. And according to Einstein, energy of photon is given by E equal to mc square, where m is the mass and c is the velocity of photon. Velocity of photon. Now if we compare equation first and second, we get mc square is equal to h nu. But we know nu equal to c upon lambda, where c is velocity of photon and lambda is wavelength. So we can write like this: mc square h c lambda. Now c they cancel out and we get mc equal to h upon lambda, or lambda equal to lambda, when this transpose each other, we'll get lambda equal to h upon mc. But c is the velocity of photon. But if we change it with velocity of electron, we can write lambda equal to h upon mv, or we can say lambda equal to h upon p, momentum. So this is the complete derivation, and let's see it the other way. Let's repeat it. According to Planck, energy of photon is given by the relation E equal to h nu, where h is Planck's constant and nu is the frequency of radiation. And according to Einstein, energy E of a photon is given by the relation E equal to mc square, where m is the mass and c is the velocity of photon. Comparing the relation first and second, we get mc square equal to h nu, where I have told you that nu is equal to c upon lambda, and when we replace the nu with c upon lambda, we get this relation. And here c and c square cancel out, we get mc equal to h upon lambda. And now transposing these two, we get lambda equal to h upon mc. This is our third relation. In equation 3, replacing c is the velocity of photon, by v, that is velocity of electron, we have the final relation lambda equal to h upon p. So from this relation of de-Broglie, we can find the wavelength, we can find the momentum or mass or velocity. So equation 4 is de-Broglie's equation and is verified by Davison and Germer. It holds good for all particles like electrons, protons, neutrons, atoms, molecules, etc. Now the verification of dual nature, that is wave nature. Davison and Germer experiment. In this experiment, diffraction pattern of electrons was same as that of X-rays. Since X-rays possess wave nature, thus electrons must possess wave nature, and the Davison and Germer found the diffraction pattern of both electron and X-rays is similar. Since X-rays possess wave nature, Thus, the electrons must possess the wave nature. This verifies the dual nature of electrons. Now, let's see a question that find the wavelength of an electron moving with the speed 2 into 10 raised to the power 6 meter per second. We have to find the wavelength of the electron, and we can use the formula lambda is equal to h m v. So we know velocity of electron is given, that is 2 into 10 raised to the power 6 meter per second, and mass of the electron is known to us, m is equal to 9.1 into 10 raised to the power minus 31 kg, and Planck's constant has a fixed value, that is 6.63 into 10 raised to the power minus 34 joules. The de-Broglie wavelength is given by the formula. So, after putting the values of h, m and v, we get the value of the wavelength, that is 0.364 into 10 raised to the power 9 meters. And that's all.
Heisenberg's uncertainty principle. This is a topic from 11th class chemistry, unit 2nd, that is structure of atom, and I am your teacher Shakti Kumar. Let's start. So, Heisenberg's uncertainty principle. You know that trajectories of all moving objects like cars, planets, balls, etc., when move along definite paths or trajectories, position and velocity can be measured accurately at any instant of time. जब कोई कार अपने एक सर्कल में घूम रही है, या कोई बाल हम फेंकते हैं, या प्लैनेट्स जो अपने ऑर्बिट्स में घूम रहे हैं, तो उनकी जो ट्रैजेक्टरीज हैं, उनकी पोजीशन और वेलोसिटीज जो हैं वो एक्यूरेटली मेजर हो सकती हैं एनी इंस्टेंट ऑफ टाइम, किसी भी समय. एंड but for subatomic particles like electrons, protons or neutrons, it is impossible to measure accurately their velocity and position accurately. So Werner Heisenberg in 1927 gave the uncertainty principle, known as Heisenberg's uncertainty principle, which was based upon this concept that position and momentum can't be measured accurately for subatomic particles. So, the principle behind the uncertainty principle, it is impossible to measure simultaneously the position and momentum of small particles like electrons, protons, neutrons with absolute accuracy. And if attempt is made to measure any one of these two quantities with higher accuracy, the other one becomes less accurate. तो इसमें ऐसा है कि अगर एक चीज हम मान लो हम पोजीशन को एक्यूरेटली मेजर कर रहे हैं तो उसका जो मोमेंटम है, मोमेंटम जो है वो बिगड़ जाएगा। अगर मोमेंटम को हम एक्यूरेटली मेजर कर रहे हैं तो उसकी पोजीशन जो है वो एक्यूरेट हमें नहीं मिलेगी। सो द प्रोडक्ट ऑफ uncertainty in position, this is uncertainty in position, and uncertainty in momentum, where h is Planck's constant. So product of uncertainty in position and momentum is greater than or equal to h upon 4 pi. So the principle is the product of uncertainty in the position, that is delta x, and uncertainty in momentum, that is delta p. Delta p can also be written as m delta v. So where m is the mass of the particle and delta v is uncertainty in the velocity, is always constant and equal to or greater than h upon 4 pi. So product is always constant, which is equal to or greater than h upon 4 pi, where h is Planck's constant and the value of p can be calculated by the given value of delta x and vice versa. So if we put this value for delta p, that is m delta v, in equation first, now the equation will become like this. Here instead of p delta p we will write m delta v, and this is our new value. And finally if we rearrange we get delta x into delta v greater than equal to h upon 4 pi m. So this is our final equation, delta v greater than equal to h upon 4 pi m. Now the explanation. The Heisenberg's uncertainty principle, delta x or delta p equals to h upon 4 pi, or we can write it like this also. If we replace p with v, then the equation will become like this. So it can be written as delta x delta v greater than equal to h upon 4 pi m. Now in this equation, this implies that the position and velocity of a particle can't be measured simultaneously with certainty. If delta x is very small, if delta x is very small, very low, position can be measured accurately. So position can be measured accurately. If delta x is very small, position can be known accurately. But delta p being very large, very high, delta p being very high means momentum or velocity can't be measured. Momentum can't be measured. if delta x is very small, position can be measured, but momentum can't be measured. Right? Here in this case, delta x is very low and delta p is very high. So position can be measured. Position can be measured accurately, but momentum can't be measured. So in next case, if delta p is very small, that means no momentum and velocity can be measured accurately. When delta p is now very small, so momentum can be measured. No momentum can be measured, but uncertainty in measuring the position. But position can't be measured accurately now. Here position can't be no, because it becomes very high. Uncertainty in position becomes very high. If delta x is 0, now if delta x is 0, position is located accordingly. Now if delta x is 0, position can be measured accordingly, but momentum and velocity can't be measured accurately at all. At this point, when delta x is 0, position can be measured accurately, but momentum and velocity can't be measured accurately. What is the significance of uncertainty principle? For seeing an object, we know in order to see an object, the illuminated light reflected and reaches the eyes, object becomes visible according to the principle of optics. किसी भी चीज देखने के लिए उस पे लाइट जब पड़ती है और वो रिफ्लेक्ट होकर लाइट हमारी आंखों तक पहुंचती है, तो तभी हम उसको देख सकते हैं. यही ऑप्टिक्स का प्रिंसिपल है. सो फॉर शॉर्टर वेवलेंथ, ग्रेटर एक्यूरेसी इन मेजरिंग पोजीशन. जब वेवलेंथ शॉर्ट होगी तो पोजीशन मेजर करने की एक्यूरेसी वो ज्यादा होगी, बट इम्प्लाइज हायर मोमेंटम. लेकिन उसके लिए मोमेंटम काफी हाई रहता है. इम्पार्ट्स ग्रेटर मोमेंटम ऑफ इलेक्ट्रॉन, रिजल्ट इन ग्रेटर अनसर्टेनिटी इन वेलोसिटी. ठीक है, अगर वेवलेंथ शॉर्ट रहेगी तो ग्रेटर एक्यूरेसी इन पोजीशन. पोजीशन में तो एक्यूरेसी आ जाएगी, लेकिन मोमेंटम बढ़ने की वजह से वेलोसिटी में अनसर्टेनिटी आ जाएगी. और अगर मोमेंटम को डिक्रीज किया जाए, अब दूसरी बार है कि मोमेंटम को डिक्रीज किया जाए, तो इसका मतलब अब वेवलेंथ जो है उसको इंक्रीज किया जाए. पहले वेवलेंथ शॉर्टर थी और वेवलेंथ जो है उसको इंक्रीज किया, लॉन्गर वेवलेंथ, तो ग्रेटर अनसर्टेनिटी इन मेजरमेंट ऑफ पोजीशन. अब अनसर्टेनिटी कहाँ पे आ गई? पोजीशन को मेजर करने में, जबकि पहले केस में पोजीशन जो थी वो एक्यूरेटली मेजर हो रही थी. अब हम क्या कर रहे हैं? वेवलेंथ को इंक्रीज कर रहे हैं, तो पोजीशन को मेजर करने में अनसर्टेनिटी आ रही है. So both position and velocity can't be measured accurately. If we control one and lose the control on other, एक को कंट्रोल करते हैं, दूसरे का कंट्रोल खो देते हैं. Now let's take a question. What is the uncertainty in the speed of a proton if it is desired to locate its position within uncertainty of 4.91 nanometer? So here we have to find uncertainty in speed of a proton if it is desired to locate its position. Its position is given. Position within an uncertainty of x equal to 4.91 nanometer. So the solution for this problem, let's first identify the given information in the problem. So first of all, what is given to us? that is uncertainty in protons position. Uncertainty in protons position is given, that is delta x. Uncertainty in position is denoted by delta x, and its value is 4.91 nanometer, which we can also write in meters, like 4.91 into 10 raised to power minus 9 meters. And Planck's constant, that is a constant value of h, which is 6.626 into 10 raised to the power minus 34 joules second. And then mass of the proton is known, which is 1.67 into 10 raised to the power minus 27 kg. Now we have got this much of information, and now we will substitute these values in Heisenberg's uncertainty principle, which is given by an equation, that is delta x into delta p equal to h upon 4 pi. So here delta x is given, h is given, pi's value we know. Now here we can also write delta p like this. Delta p can be written like m delta v, m delta v. Then the equation becomes like delta x into m delta v, where we have replaced delta p with m delta v, which is equal to 4 pi, h upon 4 pi. So we can also interchange delta x and delta v. So now the equation becomes like this: delta v equal to h upon, this goes here, and delta v equal to h upon 4 pi m delta x. Now after substituting the values of h, pi, m and delta x, we can get the value of delta v. So let's substitute the values and see what's the result. We know that delta v is uncertainty in the speed of the proton. Thus, after substituting all the values and after simplifying, we get delta v equal to x.43 meters per second, which is the uncertainty in the speed of the proton, which we have to find. Okay, so that's all.